right, this lecture will cover the procedures of slices, which is the most common way that slope stability is analyzed today using computer solutions. So what we'll do is start with a circular slip surface. You could use procedure of slices with non-circular slip surfaces too, but usually we do circular, and I'll just stick with that for this derivation. But it's easy to extend it to other types of surfaces. So what we'll do is, here's the center of the circle and the radius, and then we draw in the failure surface and divide it into vertical slices. So here I've drawn these dashed lines to represent all of the different vertical slices that we have. And then if we look at a particular slice right here, you can see that there are some forces acting on it. There's the weight of the slice acting downward. There's a normal force and a shear force. A normal force N and a shear force T acting at the bottom of the slice. And the base angle of the slice is alpha. So that's a lowercase alpha right there. And then I labeled this slice, the base length is delta L. It would have been a little crowded to label this slice, but anyway, this would be like delta L, maybe I should add an index, I plus 2. So I would be like, this is the ith slice, I plus 1, I plus 2, and then you'd have I minus 1, I minus 2, and so forth. Okay, and in this case, we have n number of total slices. Maybe we should change that to be like n sub s, because we're already using n for the normal force. Oftentimes we divide the slope into like 20 slices, something like that. You can use more, you can use fewer. You just want the slices to basically represent the geometry of the problem accurately. Although we're using a circle here, what generally happens is that we discretize the slices into trapezoids, right? So we're going to approximate the shape of the bottom of the slice as a straight line. So if you discretize too coarsely, you're not going to get a super accurate representation of that circular surface. Okay, and then there's a distance, A, at the top. That's from the center of the circle to the weight of the slice. Another thing that we usually do with the method of slices is we assume that the slice width is pretty small, in which case we can just put the weight right at the center. All right, in reality, this weight would act slightly to the left of center just because that kind of trapezoidal shape is shifted to where there's more mass on the left side than the right side. But if we use enough slices, that that difference in distance doesn't really matter. And I've only drawn about 12 slices or something like that here. In reality, they would be even thinner, and so you can see that it's really an okay assumption to treat it as a trapezoid with the weight acting at the center. For coordinate system, I'm going to do z vertical and x horizontal, and then counterclockwise is positive for moment. We're going to do moment equilibrium about the center of the circle for finding the factor of safety. All right, so down here, and then here's the radius, right? The constant radius of the circle. So if we solve for moment equilibrium about the center, there's going to be two different moments that we can compute. One is the driving moment, and that's going to be due to the weight of the slice acting through a distance A. And A is measured, A can be negative, so this is something that is often a little confusing. I'm going to have a positive A being as shown right here, and then a negative A would be to the left. And, you know, that's consistent with the coordinate system. Positive X is to the right. So this weight acting at a distance of positive A will produce a clockwise bending moment. Therefore, it's a negative bending moment, right? Because our sign convention is that counterclockwise is positive. So what we have is that the driving moment is equal to minus the summation of all of the weights times the distances through which those weights act. And what we can do too is use trigonometry, right? We have a little triangle here. The hypotenuse is R. It's a right triangle because this top angle is a right angle, and the short length is A. So A is equal to R times sine alpha. So we can make that substitution right there. We get R sine alpha. And then, of course, we have the summation over here, and those should be, let me update that, n sub s, number of slices. Okay, so the summation is over all of the indices with an I on it, but R is a constant, right? The radius is the same for every slice, so we can pull it outside the summation, and you just get minus R times the summation of Wi sine alpha I. All right, now the resisting moment is equal to this T term right here multiplied by R, which is that distance. And that's going to be a positive moment because T is going to act from left to right as drawn there. So the resisting moments are the sum of R times Ti. And then we can represent this T as a shear stress instead of a shear force just by dividing by the base length of the slice. Okay, the width would be measured horizontally. That's usually called lowercase b. Delta L is actually the base length measured along the angle alpha. So here you would have R times the summation of tau I, delta L of I, and then we can substitute in our expression for shear strength here for tau. Recall that tau is equal to the shear strength divided by the factor of safety, right? It's the equilibrium shear stress. So there's our expression. Oops, here we go. There's our expression for shear strength divided by factor of safety. So we've just substituted that for tau. All right, now the sum has to be equal to 0 in order to have moment equilibrium. And if we add those together, set them equal to 0 and solve for f, we get this equation right here. I'm skipping some algebra, but it's fairly straightforward to see this. And I'm now getting rid of the summation being from I to n sub s, just because it's implied, right? We know that that's in there. It's kind of a drag to write it over and over again through these equations. So anyway, we get a summation of the shear strength times delta L divided by the summation of W times sine alpha. Now, if phi is equal to 0, we can get rid of this term right there. We get rid of the sigma sub I term, which has a lot of benefits, actually. It simplifies the expression a lot, so it makes it much easier. And now we've reduced it to being exactly the same as the Swedish circle method. So you could solve this problem using the Swedish circle method as a single free body if you wanted to. But again, it's difficult to come up with the properties of that free body in terms of the weight and the center. So you'd probably divide it into vertical slices anyway. So even though it's equivalent to the Swedish circle method, we usually would solve it using a method of slices anyway. All right, if you have this sigma in there, then you have to know the normal force too, right? If we're doing Swedish circle, all you need to know is the shear force acting on the bottom of the slice. And you can sum all of that up, and you don't have to worry about the normal forces, which makes it kind of nice. What that means is that, you know, what we're going to show later is that we have to make some assumptions about how these slices interact with each other. Those assumptions have an impact on how big the normal force is at the bottom of the slice, and therefore it has an impact on how much shear strength you derive from the friction term in the Mohr Coulomb failure envelope. And you'll get different numbers for the normal force for different assumptions, and so you get slightly different answers for the problem. If phi is equal to 0 and the friction term doesn't exist, then we've gotten rid of that sigma. All the assumptions that we have to make don't actually influence the problem anymore because the cohesion term is constant or the end-range strength is constant, and you'll get the same solution regardless of which procedure of slices you use. It's because it's the Swedish circle method. All right, let's take a look at the free body diagram for a slice. It turns out that this problem is statically indeterminate, and I want to show that to you, and what that means is that we have to make assumptions. We don't have enough equations, and we get our extra equations by making assumptions about how the slices interact with each other. So here's the free body diagram. We have the weight, we have the normal force and shear force, which are things that we've already seen previously. And then there are forces acting on the sides here too. There's going to be a horizontal force or normal force on the sides and a shear force on the sides. So we have E and S. And then there's E plus 1 and S plus 1. So if we look at this slice, we have three equations, right? You can sum up moments, that looks like a lambda, it's an X. Sum up moments in the X direction, Z direction, so two force equations and one moment equation. And you can sum moments about any point, right? If it's in equilibrium, it's in equilibrium about any point. Okay, but we have 6 unknowns for this particular slice: T, N, E, I, SI, E, I plus 1, and SI plus 1. Now, once we extend this to the overall free body diagram, we can actually reduce the number of unknowns a little bit, because notice that by symmetry, EI has to be equal to minus E of I minus 1. So if you had another slice over here, right, you would have the EI plus 1 for that slice is equal to EI, or EI is equal to minus EI minus 1. Similarly, the shear forces have to be equal and opposite as well, just by symmetry. So there's really only 4 unique unknowns per slice. But that doesn't help us because we still only have 3 equations, so we can't solve this problem. So let's do a little example just to illustrate how many assumptions we have to make here. Here's an example that shows just like this this is non-circular, although I guess you could argue that, there might be a circle like that, and we just haven't done a very good job of discretizing it into slices. So this could be representative of a circular surface, but anyway, the purpose is just to illustrate equilibrium. It's not to model a real slope or anything. So for slice number 1, we have the N. If you look down here, you have N and T, and then you have the weight, and then there's no E on the left side because there's no vertical slice boundary on the left side. Okay, on the very left side of the problem, the failure surface has to daylight, and therefore you don't have a vertical boundary there that's going to have a force acting on it. So E1 and S1 are right here just on the right side. Then, of course, those are equal and opposite, so the slice is acting on the left side of slice 2, and you would have E2 and S2 acting on the right side, and obviously you have W2, N2, and T2. And then E2 and S2 also act on the left side of slice 3, and slice 3 similarly daylights at the top of the slope, so there's no E3, S3 acting on it. You just have E2, S2, W3, T3, and N3. So we know W1, W2, and W3 because we have to know the unit weight of the soil. We know the areas of those slices, so it's easy to compute them. And we have 9 equilibrium equations. For each slice, we can sum forces and moments. And in this case, we have 10 unknowns, right? There's N1, N2, and N3, T1, T2, and T3, and then there's E1, E2, and S1, S2. So still, that's too many unknowns for us to solve, given the equations that we have available. And what that means is we have to come in and make some kind of assumptions about these E's and S's in order to give us one more equation up here, so that we can render a we can render a solution. So what this means is the problem is statically indeterminate, right? We can't solve it based on statics alone. We have to make some additional assumptions in order to facilitate a solution to the problem.